Good evening, everybody. I am Vibhu Swain from Power Tech Consultant. Today we'll start our webinar number 30. Let me share my screen with you. So in this webinar number 30, we'll complete the remaining portion of mass and energy balance, which is chapter 5 of book 1, that is general aspects of energy and management and energy audit. We have already studied about mass balance and energy balance. We have solved some numericals on mass balance and energy balance as well. Now let us understand how can energy be lost in a systems. For example, as I told you earlier, energy cannot be created nor destroyed. So how is energy is lost? Or if energy cannot be created or cannot be destroyed, then what is the use of saving energy? Then why we conserve energy? Basically, we conserve the useful energy, or so that useful work can be done. But there are not lot of non-useful energy, or we cannot utilize all the energy fully for useful work done, due to which some energy is lost. It might be due to friction, it might be lost to the surrounding as heat energy, it might lost to it might get lost due to different accounts which you cannot calculate. So there are some unaccounted energy is also lost. So because of various reasons, the energy can be lost. All the energy is not converted into the useful work, and our aim is to reduce this energy loss and increase the useful energy, so that energy can be utilized fully. Now, energy can manifest itself in many forms: heat energy, kinetic energy, chemical energy, potential energy. But because of these interconversions, it is not always easy to isolate separate constitutive energy balance. Because during a process, it can take any form. It can take form of heat, it can take form of any different types of chemical energy or storage energy. So it is difficult to do energy balance. Now, energy is lost means it changes into a form that is not counted. We cannot count it, or we cannot monitor, or we cannot calculate. So, due to which we call it energy is lost. Most often, the unaccounted energy is worked on against friction. Basically, it is lost in friction and as heat energy. This work changes other form of energy into heat and wear. So what we get end result either heat or wear and tear of the component. No energy is lost in the end, only forms have changed. So basically the forms get changed. This loss of usable energy is due to many causes. In mechanical system, it is friction. In electrical system, it is resistance. In fluid system, it is turbulence, viscosity, or mixing. So these are the ways how energy is lost. Practically, approach to energy balance takes into account only heat balance, ignoring internal energy. Because in a closed loop, we assume that internal change in internal energy is zero. So we only account the heat balance. When we are unfamiliar with the relative magnitude of various forms of energy, oil, gas, coal, steam, chilled water, and electricity, entering or exiting a particular processing situation, it is best to put them all down and convert them to equivalent heat energy. That means since energy balancing is complex and internal change in internal energy in a process is zero, therefore, in order to do energy balance, what you do? We do heat balance, in which we convert all form of energy into heat unit, and and we conduct the heat balance of a plant system. Now, heat balance enthalpy, that is the total heat is conserved as with the mass balance. Enthalpy balance can be written around various items of equipment process stage around the whole plant. It is assumed that no appreciable heat is converted to other form of energy such as work. That means all the heat energy, input energy, and is equal to output energy. So all input heat is equal to output heat. So heat balance is normally carried out for all the plant or for equipment or for any process. Enthalpy always refer to some reference label or datum. So the quantity is related to the datum. We calculate the enthalpy related to certain datum or reference point. Working out energy balance is just then a matter of considering various quantity of material involved. What do we require? The material involved, specific heats, the change in temperature or state change or the latent heat. So if we have all these informations, then we can carry out the heat balance or enthalpy balance by considering any reference level. Now, facility as an energy system or plant energy systems. So in a particular any industries or any plant, how is the energy systems? Let us understand it. In a production facility, the energy is in form of coal, oil, gas, electricity enter the facility is converted to more convenient form of energy such as steam, compressed air, chilled water. The outgoing energy is usually in the form of heat and motions. So this is basically the energy system of any plant. What it does exactly? Now, what is the primary energy? Coal, oil and gas. What is the secondary energy? Electricity. These are the basically energy input to any systems. We don't require this energy. We require the derivatives of the energy. Or what exactly we require? So these primary and secondary energy goes into the energy conversion process. Electricity goes to transformer, it is stepped down and utilized in the process. Oil goes to degenerate, it generates power. Coal goes to boiler, it generates steam for power generation and for process heating. Electricity goes to into chillers. We get some chilled water for our process requirement. Water supply, we require DM water, hot raw water, and other water, service water. Then electricity goes to air compressor, we get compressed air. So these are the utilities. So energy input, this is the energy facility or utilities in which energy conversion happens. Then we get the product of utility, that is electricity, steam, thermic fluid, chilled water, DM water, cold and hot air, compressed air. Now this is your production process where we get the raw materials. This is a production facility. This energy or the utilities are utilized and we get the output product. Some energy is carried out with output product and heat goes, this heat goes in products, flue gas, water vapor, heat and emissions. So it goes as losses all along with the product. So this is the plant energy system. Now, as I told you, electrical energy is basically purchased at ST level, converted into LT supply for end use. In a plant energy systems, some plants generate their own electricity using DG set or captive power plant. Fuel such as furnace oil, coal are purchased, then converted into steam and electricity because these are purchased. Boiler generates steam for heating and drying demands, also for power generation for driving the turbine. Cooling tower and cooling water supply water system for cooling demand. Air compressor and compressed air supply system for compressed air needs. All energy system can be classified into three areas: generation, distribution, and utilizations for system approach and energy analysis. So basically, this is your plant energy systems. Now let us solve these problems. A furnace cell has to be cooled down from 90 degrees centigrade to 55 degrees centigrade. The mass of furnace cell is 2 tons. The specific heat of furnace cell is 0.2 kilocalorie per kg degree centigrade. Water is available at 28 degrees centigrade. Maximum allowed increase in water temperature is 5 degrees centigrade. Calculate the quantity of water required to cool the furnace. We have to assume that there is no loss, so neglect heat loss. This problem can be easily solved by applying heat balance method. Now, let us do energy stream 1. So, what is the mass? 2 ton, that is 2000 kg. Specific heat 0.2 kilocalorie per kg per degree centigrade. Initial temperature T1 is 90 degree. Desired furnace cell temperature is 55 degrees centigrade. That means we need to cool the furnace cell by using cold cooling water. So what will happen? Furnace cell temperature will go down and cooling water temperature will go up. But cooling water temperature cannot go rise. Change in temperature should be less than 5 degrees centigrade. Now, total heat that has to be removed from the furnace will be what? MST theta, that is MCP T1 minus T2. So from this, we found out 2000 into 0.2 into 90 minus 55. So this is the heat need to be removed from the furnace. Who will remove it? The cold water will remove it. What is the input energy? Let this, it has been asked, what is the quantity of water? Now let us assume that quantity of water required is x kg. Specific heat of water is 1 kilocalorie per kg per degree centigrade. Now what is the input temperature of water? 28. Now maximum allowable change in temperature is 5 degrees centigrade. So maximum cooling water outlet temperature will be 28 plus 5, 33. So x removed by water will be x into 1 Cp into 33 minus 28. So this is basically 5x kilocalorie. So as you know, energy balance means quantity of energy stream 1 is equal to energy stream 2. So quantity of x will be this one by 5. So 2800, that means 2.8 ton of water is required for cooling this furnace. So this furnace problem can be easily solved by applying energy balance. Now let us do a dryer heat balance. Dryer basically utilize, it takes oil or coal or hot gas or electrical heating, then dry the raw materials or dry the cloths. So this is basically dryer in which input energy, heat energy given, and it dries the product output. The textile dryer is found to consume 4 meter cube of natural gas with calorific value of 800 kilojoule per mole. If the throughput of the dryer is 60 kg of wet cloth per hour, drying it from 55% moisture to 10% moisture, estimate overall thermal efficiency of dryer taken into account of latent heat of evaporation only. So what has happened? The dryer now, what is the system input cloth? 60 kg of wet cloth per hour. Now moisture content is 55%. So initial moisture in the wet cloth is becomes 60 into 0.55. That is 33 kg of moisture is there in the initial process. Now bone dry cloth is basically 60 into 1 minus 0.55. That is 27 bone dry cloths. So basically, so the cloth weight is basically 60 minus 33, that is 27. Now, the final moisture should be 10%. That means the final product moisture content is 10% means it will be 27 by 9, that is 3 kg. So moisture removed is 33 minus 3, that is 30 kg per hour. That means this problem can also be solved by applying mass balance. So if 27 is there of dry cloth, that means in the dry cloth remains same, and moisture is 10%. From this, we can calculate by applying mass balance also that the final product moisture content will be 3 kg and moisture removed will be 30 kg per hour. Now, what is the latent heat of evaporation? Is 2257 kilojoule per kg. So, heat used for drying cloth will be 30 into this latent heat. It is 6.8 10 to the 4 kilojoule per hour. Assuming natural gas to be standard temperature and pressure, at which 1 mole occupies 22.4 liter. Now, rate of flow of natural gas is 4 meter cube per hour. So, that means 179 moles per hour, because from this 4 into 1000 by 22.4 liter. So, heat available for combustion is equal to 179 into 800, because the calorific value of natural gas is 800. It becomes 14.3 into 10 to the 4 kilojoule per hour. So, what is the input heat energy? This much. What is the output heat energy used? It is 6.8 into 10 to the 4. So, what is the thermal efficiency of dryer? Input heat, output heat is equal to output input heat. So, 6.8 by 14.4, it becomes 48%. So, dryer efficiency becomes 48%. Now, let us do this evaporation rate problem. Production rate from the paper machine is 340 kg, 40 ton per day. Inlet and outlet tiredness to paper machine is 40% and 95% respectively. Evaporated moisture is 80%, 80 degrees centigrade. To evaporate moisture, steam is applied 35 kg per cm square. Latent heat of steam at 35 kg per cm square is 513 kilocalorie per kg. Assume 24 days for operation. Estimate the quantity of moisture to be evaporated. Input steam quantity required for evaporation. Consider enthalpy of evaporated moisture 632 kilocalories per kg. So these are all given data. Now let us find out the solution. Now production rate from the paper machine is how much? 340 TPD. If I convert it to hour, I'll get 14.16 TPH. So input dryness to the paper machine is 40%. Output dryness is 95%. Now, how much of moisture is needs to be evaporated? 14.16 into 9.95. That means paper weight in the final product will be how much? This is a production. Production is basically 14.16 pph. So, in the production, some water is also there because it is 95% dry. So, 5% of water is also there. So, what is the paper weight only? 14.16 into 0.95, that is 13.45 dph is the paper weight. Now, weight of the moisture before dryer is how much? 100 minus 40 by 40 into 13.45 is equal to 20.175 dph. So, weight of moisture before dryer is this much. This can be also be found out by applying mass balance. So, weight of moisture after dryer will be how much? 14.16, because this is the production rate, into 0.05. So, weight of the moisture is 0.707 ton per hour. So, what is the evaporated moisture quantity? 20 minus this. So, initial moisture divided by final minus final moisture. So, this is the moisture needs to be removed. Now, here what we have applied? We have applied mass balance formula. If you solve it also, we'll find out these numbers. Now, evaporated moisture temperature is how much? 80 degrees centigrade given. So, and enthalpy of evaporated moisture is 632 kilocalories per kg. So, heat available in moisture is becomes sensible for latent is 632 into 19,468 kg. So, this is the heat available in the moisture. Now, for evaporation, minimum equivalent heat available should be supplied from steam. So, latent heat of the supply is steam at 3.5 kg per cm square is equal to 113 kilocalorie. So how much of steam will be required? This is the energy divided by enthalpy of steam. So 23.98 ton of hour TPH of steam is required. Now by doing mass balance, by doing energy balance, we can calculate the boiler capacity. How much of steam required and what is the boiler input or boiler rating should be for this process. So based on the moisture removal, moisture percentage, knowing the different gross calorific value of steam as well as the fuel, we can calculate what is the steam energy required. Now, what do you do? What do you mean by Sanket diagram? Basically, it is a tool. Now we do energy analysis. We don't know which energy is very high, where the energy loss, where energy is getting wasted. Now all this energy analysis, the output needs to be presented to management. This can be easily done with the help of Sanket diagram. Now Sanket diagram is a tool to represent an entire input and output energy flow in any energy requirement system such as boiler generation, fire heaters, furnace after carrying out energy balance calculation. So this is a tool. This is only a graphical tool which depicts the energy system or energy balancing. Now in this tool, energy flows are represented by arrows. The width of the arrow is proportional to the size of axial flow. If the flow is very energy flow is very high, then the width of the arrow will be bigger. Now, better now we have normally we do energy analysis by Excel, by numbers, by table, by descriptions, by writing lot of words, but it is very difficult for us, the management to understand. So what we do, we draw a diagram that is known as Sanket diagram. Now the basic data needed for energy analysis are energy input, energy utilized, and energy distributed or wasted. Now if I have these data, I can plot a Sanket diagram. The energy balance of each process section is easily best represented by a Sankey diagram. So how it looks like? You see 100% fuel energy. This is a combustion. Now these are a green energy because 25% effective power. This is a useful energy. That's why the color is green. Now this is the we see the width of the this flow 25%. So width is moderate. 5% friction and parasitic loss. That means this 5% is the width is comparatively lower than this. Now this is in red. Why? Because these are lost energy. 30% who is taking? Coolant is taking. So you see this width, it is bigger than this. Now 40% exhaust gas means all the exhaust gas is going to the atmosphere through the chimney. So what exactly is this? This width is more as compared to this. That means we have to do lot of energy conservation project, do lot of study and monitoring in the gas loss. So this is the information we are coming, the management is able to know, and that's for Sankey diagram is an important diagram as far as energy analysis is concerned. Now exhaust flue gas losses are key area priority. Now this is exactly we have discussed. Now what we can do, how to reduce the exhaust gas loss? If we can utilize some steam recovery or the heat waste heat recovery system in this process, or we can utilize the set energy in the cooling water circuit for vapor absorption evaporation systems. So these are the ways how we can utilize this waste energy, and this can be easily represented with the help of Sankey diagram. Now we shall solve one problem. An evaporator is to fed with 10,000 kg per hour of solution having 1% solid. The feed is at 38 degrees centigrade. It is to be considered at 2% solid. Steam is entering at total enthalpy of 640 kilocalories per kg. Condensate is at 100 degrees centigrade. Enthalpy feed is 38.1 kilocalories per kg. Product solution is 100.8 kilocalories per kg. That of vapor is 640 kilocalories per kg. Find the mass of vapor found for what hour, the mass of steam used per hour. So this is what we have to solve. Now what is the feed? 10,000 kg per hour. Now it is contain 1% solid. So how much of solid? 10,000 into 1% becomes 100 kg per hour. So mass out will be how much? 2% solid. So mass out is 2% solid. That means mass out will be 10,000 by 2, that is 5,000 kg per hour. From this material balance, we can find out what is the, for 2%, what is the mass output. Mass out will be 10,000 by 2, it becomes 500 kg per hour. So that means what happens? This 10,000 flow is coming down to 5,000 flow. That means around 10,000 minus 5,000, 5,000 kg of vapor is formed. Now, so thick liquor is 500 kg per hour. Now, enthalpy of feed becomes how much? 10,000 into 38.1, because this is the 10,000 is the enthalpy, feed and feed temperature is 38. So enthalpy of thick liquor will be 100.8 into 5,000. Why? Because this is a vapor formed is 5,000, and what is 100.8? 100.8 we have come from the product solution is the enthalpy of product solution is 100.8 kilocalorie per kg. Now, what is the enthalpy of vapor? Vapor weight is 5,000 kg per hour. Enthalpy is 640. So, enthalpy of vapor becomes 32 lakh kilocalorie. Now, if I do have to heat balance, what I'll do? And heat input by steam plus heat in feed. That means, let us assume the mass is m. So, heat input by steam is 640 minus 100. 640 minus 100, because the condensation lived at 100 degrees centigrade. Now 38.1 into, that is the heat in feed. 38.1 means enthalpy of feed, and what is the heat output in vapor is equal to 32 kilocalorie, and enthalpy of thick liquor 5.04 kilocalorie. So from these, by putting all this formula, we can find out what is the mass of steam required. That will be 3323,000 by 540. What is the enthalpy of that vapor? So we can know, or enthalpy of the steam. So we can know the mass of steam required will be 6153.7 kg per hour. So basically, mass and energy balance, we have to solve a lot of numericals. Then only we can control this. And otherwise, there are few theories like what is mass balance, what is energy balance, what is Sanket diagram, what do you mean by energy loss, and plant energy system. SKI plant energy system, maybe 10 marks. So with this, I conclude the chapter 5 of book 1. I request you all to solve numericals so that you can attempt and you can score easily in this chapter. With this, I conclude. Good night.